So I'm not sure quite how much this talk has to do with asset management, but the point of it, I guess, is you know, as Anna says, to give you an idea of what's coming up in the sort of one avenue of the interoperability and blockchain architecture and technologies direction. So yeah, I'm kind of fairly busy these days coding up Substrate and Polkadot. And if you're not familiar, I'll reiterate, Polkadot is a network protocol designed to allow lots of different blockchains to sort of talk to each other. But they talk to each other in a way that you get certain guarantees, and those guarantees allow the blockchains, allow the conversation that they're doing to be sure that, you know, if they say something like, I transferred this asset to you, then you can be sure that the asset was indeed transferred. So what the two things that we talk about when we're talking about cross-chain communication is validity and finality, right? So validity is this notion that when a chain says, I did this thing, then they actually really did do it. They're not just lying to you, right? So there is some notion that a particular state transition occurred. For example, the asset might be destroyed on the chain that's saying, I transferred this asset to you, so that the chain that's receiving the message can create it without sort of wondering whether they might just have created another asset and therefore added something to the total issued assets. Whereas in fact, because they can trust that the message is true, they can be sure that the total issued assets remains the same. And finality is the notion that when one chain accepts and interprets and executes on a message, that the chain that emitted the message in the first place doesn't then later get reverted to the point that the message was no longer issued, which of course would be a huge problem if you issue a message saying, yeah, I destroyed this asset, please mint a according asset on your chain. And then suddenly that was reverted, so they never destroyed the asset in the first place, but the asset was nonetheless minted on the destinations chain, then you have now two assets where there should only be one. So that's what Polkadot looks after. Substrate is a framework for building blockchains. It happens just so to work quite well with Polkadot. And the talk is mostly about where we are with Substrate and what's coming up in the sort of next year or so for both of the projects. So a brief history of Substrate. Oh dear, oh dear. I'll have to go over, yes, go over what's meant to be there. I guess something wrapped when it shouldn't have done. Right, so back in first half of last year, we released the first version of Substrate, and it had these technologies associated with it. It used this consensus mechanism called rhododendron, which was fairly similar to Tendermint, if you're familiar with that, or built upon PBFT, a well-understood means of making sure that a group of actors come to a consensus given a limited number of bad actors among them. It had an interesting random number generator called the collective coin, collective coin flip, and it's to do with, I won't go into that, but it's a relatively simple means of generating a random number. It had a very simple proof of stake mechanism. Transaction signing used the ED 25519 signing mechanism. I don't know if that means anything to anyone here, but it's kind of cool, but we kind of improved it later on, as you'll see. Networking used the very old networking protocol, the same one as Ethereum, didn't have a light client, had a very basic WebAssembly environment, and the governance, well, was actually fairly decent, but we improved upon it later. For the POC2, we introduced slashing, and we switched the networking layer over to libp2p. And for the beta, the 1.0 beta that we released at the end of last year, we switched to our new consensus technology, which we're very, very proud about. Grandpa is the consensus. I can't remember what it stands for, but it was very, very creative. Yeah. For the production, we use a very simple mechanism called Aura, which I won't go into either. And for slashing, we introduced this kind of new punishment mechanism that makes sure validators that are misbehaving get kicked off fairly quickly. We had a light client then as well. And the governance was kind of interesting. We introduced this kind of bonus for hodlers. So originally the governance was a very simple kind of referendum coin vote style thing, where basically anyone who had some coins on the network would be able to either back or reject a particular motion. The motion could do basically anything. And that's kind of cool, but it's got a lot to be desired, and I'm sure there's plenty of people that have that you may have listened to Twitter feeds or talks sort of saying about how bad coin voting is. So we introduced a couple of kind of amendments to that scheme, which I'm pretty proud of. So one of them is the Huddle Bonus, which basically means if you hodl your coins, you get a bonus in your voting power. And the particular way it works is for every 2 weeks extra you agree to hodl beyond the vote, you get a sort of an extra amount, an extra vote for your coins. And we also have a delayed enactments, which works with this. And what it basically means is when a referendum, when a proposal passes, it doesn't get enacted immediately, but rather there's a period between it passing and it actually kind of, taking effect. And during that period, if, well, assuming it did pass, those coin holders that voted for it, that basically voted to make it pass, they have to hodl, right? So they have to be, they have the liability of being exposed to any of the potentially bad changes that this created, which means, in principle, we have some degree of a market mechanism so that basically the people who are against the proposal coming in can sell their coins on the market before any potential detrimental effects happen, which should therefore change the voting patterns. Going on, so at this month, or well, this month or next month, we'll be releasing the 1.0. It actually doesn't have all that much more in. Most of it's fixing reliability and bugs, that sort of thing. But the one thing that we are introducing is this new crypto, the Schnorr Ristretto version of the 25519 curve. And yeah, well, what it does is basically gives you soft HD key derivation. Hurrah, so we can basically just type in one seed phrase and you can get as many keys as you want. They can do all sorts of interesting things with these keys because they kind of link to each other in certain ways. And it has threshold multi-signature, so you can sort of create a key that's actually for which you need, let's say, 3 of the 4 keys that you've created it with in order to use it. Very handy sort of stuff. Later on this year, so over the course of the next 3 to 6 months, we'll be bringing in some new technologies. The first is Babe, to work alongside Grandpa. This will be a change from Aura. This is our sort of production-ready blockchain extension protocol. And what it does is basically a way of adding new blocks on, deciding who gets to add them, and at what time they get to add them. And it's based upon a verifiable random function that's also going to be used, as it happens, for our random number generator. I think it's like blind approval of block extenders, I think is what the BABE acronym stands for. The NPOS will also change a lot. The reason I'm actually doing this talk, by the way, is because I just came back from a sort of Polkadot Substrate research retreat, so it seemed like a very timely thing to be putting out. So all of this stuff is kind of hot off the press. Yeah, for the NPOS, for the proof of stake mechanism, we've got a couple of new technologies coming in. For the slashing, we've got correlated multi-origin slashing, which basically means depending on why someone is being punished, they can be sort of slashed in different ways. But also, the correlating bit means that if lots of people all do the same kind of malicious action at the same time, then everyone gets punished a whole lot more than if it's just one person who sort of accidentally did something wrong that was never really a threat to the network. And what this means is that it's a sort of an olive branch to validators. so that they, it reduces their risk of being, heavily slashed, heavily punished, having their stake taken off them for something that really isn't that important, something that really shouldn't be punished that much. And we've got this idea of optimal approved assignment. So up until now, the way that the staking mechanism worked was very kind of basic. I as a nominator, I as someone with a bunch of stake that I don't want to get diluted, I want to get some rewards for that stake. So I nominate a validator who's going to run a server that's going to help maintain the blockchain. I can only nominate one of them in the code so far in the various Polkadot Substrate testnets. That's problematic because, firstly, there may be several validators that I want that I'm happy with, and I have to sort of choose one of them, which is not so good. But also, it means that the general sort of market effects of which of ensuring that validators that are oversubscribed end up having their nominations sort of removed and instead transferred to lower, less subscribed validators, which overall increases the security of the network. That doesn't happen if you can only name one very easily. So instead, we've got this idea of approval voting, the approved bit of optimal approved assignment. You can't quite see assignment, there you go. And what this means is you basically approve of a number of the validators, and I don't know, maybe there's going to be 1,500 validators all with their hands out, sort of to say, hey, I'd like some of the, I'd like you to nominate me. I'd like some of your funds to back me, so I'll be more likely to actually be chosen as a validator. And what we do is we basically work out which configuration of these 1,500 potential validators can get between them the most nomination, so the most support, the most stake. Oh dear. In order that they can, in order that we can maximize the total amount of stake that we can slash in case any of them do anything wrong. There's all sorts of interesting kind of mathematical stuff that you can do, and we've got this quite nice algorithm that can do that. And the other thing we're bringing in the next few months is, we hope, pinch of salt, is the delegated voting on the governance thing. So basically, within the governance system, at the moment you have to always vote for yourself. So if you want to vote for somebody, it's basically you who always has to cast that vote. With delegated voting, I don't know how much you're aware of this kind of movement in social science, whatever, political science. But there's liquid democracy, where basically you can kind of choose someone who becomes your representative, and they can choose someone who represents them, and then of course it's all transitive. So you can the final kind of person ends up with the voting power of everyone who voted, who delegated to everyone, who delegated to everyone, who delegated to them. And that's basically what we're building. So some kind of form of liquid democracy, basically. And that covers us for the next few months. By the end of the year, with Substrate 2.0, we've got some other kind of interesting technologies coming in, and that's what I want to sort of use to talk about now. The two interesting technologies are things at the bottom right underneath the, on the WASM-env column, the WebAssembly environment. This is the environment under which all of the business logic of the chain happens. And it's it says multi and off-chain. What it means is multitasking and off-chain logic. So, yes, multitasking might also be considered as runtime parallelism, another way of saying the same thing in this instance, and off-chain compute. So I don't know, actually, the more I think about it, the more this talk is actually fairly relevant, at least to the technology builders for asset management. You'll see why soon. So runtime parallelism is, the idea of this is basically when you're executing the business logic of the blockchain, and by business logic, basically I mean just the transactions, right? Although some blockchains actually do things on a per block basis. They might have, for example, I'll give you an example, storage rent. So this notion that smart contracts can store stuff, right? And then come back to it some number of blocks later when they want to, I don't know, change a balance or finalize some agreement or whatever it is. At the moment, at least within Ethereum, storage is essentially, I mean, there's a price paid for putting something in, but you can leave it there for as long as you want. You don't have to pay anything else. And that's a bit problematic because it basically, the economics don't quite work. Yeah, it's like the cost to the network is actually keeping it in storage, not putting it in storage. So what we're doing is one of the things that we're doing sort of within Parity on our smart contracts sort of technology stack is introducing contract storage, but of course this is something that happens it's not a transaction that happens, it's something that sort of is an ongoing maintenance burden, and therefore part of the business logic for a smart contract blockchain is maintaining storage rent, ensuring that all the smart contracts are actually continuously paying rent. So I include that sort of thing in the business logic. Now for multitasking, there's a few sort of caveats. Tasks can't communicate with each other. So the reason that this is the case is because you never know what order they're going to communicate in, and it becomes non-deterministic. Yeah. So it's very, very important that the business logic of a blockchain is deterministic, otherwise different nodes on the network might come to different conclusions, and suddenly you're out of consensus. So there are sort of these important caveats that you have to sort of accept and abide by if you're going to be able to use multitasking. So one of them is that they can't communicate with each other, they can't share memory, they can't sort of share bits of their computation before they've finished, because as I say, you don't know what order they're going to do it in. Now, you can read from the storage, so they can read to see what information has been placed in storage, but they can't write to it, because if they could write to it, of course, they'd be able to communicate with each other, and that's problematic. So it's kind of like saying, to take a sort of office worker analogy, you can basically hand a bunch of office workers like a big stack of papers for them to get through, but once you handed them the stack, they go off into their own office, and they don't have a telephone or like an internet connection or mobile or anything, right? They just got to like work on this stack of paper, and eventually when they're done, they kind of like, I don't know, knock on the door or something to say, please let me out, but they can only all be let out at once, yeah? That's the sort of analogy that we're going for. So it's like kind of, prisoner office workers. Now, the idea is that this can be used, one of the things that it can be used for is to process independent transactions. They have to be independent, right? So they can't like rely on the outcome of previous transactions, because again, it doesn't work with the office worker analogy. If one office worker who's working in an isolated office A relies on the outcome of another office worker that's working in an isolated office B, well, they can't talk to each other, right? And they can only come out all at once, so how could they possibly do that? They can't. So it's important that these transactions that they're processing are independent. But there are ways of like working out whether a transaction is independent and verifying it as well. So that's not such a big issue as long as you're fairly confident that most of the transactions that you're going to be processing on your chain are indeed independent. And I reckon they probably are, but we probably need to check that. Depending on how independent they are, you're going to get like a fairly substantial improvement in throughput. So scalability, the big sort of word at the moment in blockchain. And I reckon probably, depending on the use cases, somewhere between 4 and 7x on standard sort of server hardware. Again, needs to be checked. And in case you're still really not sure what I'm talking about with parallelism, this is not parallel. So the arrow comes in, and then each box is a transaction, and it goes on the first one, and then the second one, and then the third one, and the fourth one, and it's done. This is parallel. So the arrow comes in, and then all of the boxes all get done all at the same time. And then they all get somehow kind of, amalgamated into a single result, and you're finished. So that's the first thing. And that's something that's going to help with scalability, and in general is just a sensible thing to do that we haven't really got round to yet in blockchain. The second thing is off-chain compute. And this is this has all sorts of interesting repercussions, particularly within building consensus technology for asset management. Off-chain compute is basically the idea that a particular piece of functionality, a particular piece of business logic on your blockchain has some reason or some need to go off-chain, right, to go into the wide world and do something and have it reported back to them maybe, yeah? So normally when we write like software, we don't think about what needs to be sort of done sort of on the chain and what needs to be done off the chain. Like, it's just all off the chain. It's all in the same thing. when you're doing like consensus coding, it's really tough because like you have to actually think about which bit of the code needs to remain absolutely 100% deterministically in consensus with all of the other instances of this code being run. And if your code is only operating on data that's on the chain, it really doesn't matter. But as soon as you want to sort of take in real-world data, by real-world data I mean asset prices, for example, right? Then there's a problem. It's like, right, well, the chain obviously cannot itself go off to the internet and get the asset price, right? Because it's running on everyone's computer. Everyone doesn't have a sort of absolute universal asset price service that's always going to return the same prices, right? There's maybe, I don't know, Bloomberg or whatever, but maybe their internet connection's down. Maybe Bloomberg updated sometime between one block and another block. You just don't know. You're not going to get the same price on all of the nodes. So what do you do? Well, you say, let's name 10 actors, and they can all go off to Bloomberg, and we'll choose. They can all sample what Bloomberg's saying the price is, and then they can just choose the one in the middle. They just choose the median price. All right, yeah, fine. But then who's going to write that? How's it going to integrate with a chain? How are they going to sort of send the price off? How are they going to let those guys know that a price needs to come in? And this we call the off-chain logic. And what we're doing with Substrate is we're making a very simple, very well-integrated means of writing that code, and furthermore writing it at the same sort of point that it's going to be used. So you can write both the logic that goes off to the internet or whatever and grabs the price, and the logic that uses the price in the same file, right? It's the same code in the same language using the same data structures in the same file. Basically, it means that you don't have to, the work is taken out from doing all of this off-chain integration, and it is a fairly substantial amount of work. It also means that the same server, the same node that you're using to run the chain is the software that's running this off-chain logic bit that's heading off to the internet and grabbing the asset prices or whatever. Which means in terms of your deployment costs and maintenance costs, basically the DevOps guys don't have to think about anything. They just deploy the node and it just works. Now beyond that, it's not just about oracles. Oracles are a fairly substantial use case, as you see, but there are other use cases as well. The task definition, so the logic that's doing this off-chain stuff, is stored just as WebAssembly, which means if you want to update it, you want to roll out new logic, you can do that as simply as you would send a transaction, right? Really super duper easy. And there's APIs for this particular WASM thing. So as I mentioned, you can go off to the internet, fetch a URL or whatever price feed. But you've also got other APIs, local storage. So you can store data in the node's local store and come back to it sometime later. And it's only that node that's going to be able to see that data. It's not like storing on the blockchain where everyone can see it. So you can store private data. You can store secrets. IPFS, so if you don't want to store something on the blockchain because it's too big, then, IPFS integration, so you can just store it on IPFS, come back to it later, or have some other node come back to it later that's also got IPFS running. Potentially in the off-chain bit as well. Now, if you want to, do this in a trustless fashion, so you're rolling out a public blockchain, that's where you use these things to create economic games on top to ensure that you're going to have a result that makes sense at the end of it. So simple use cases. If you want to offload CPU tasks, it's got to be something that's verifiable, right? So either you can verify it on-chain to make sure that the answer is correct. So optimization problems fall into this. Anything non-gameable, which means basically you've got to put some crypto-economic games in it to make sure that no one can just basically break it by choosing the wrong data, or anything non-critical. If it doesn't really matter whether it's that correct anyway, that fits too. If you want to offload storage, really great for archival and recall. So if you want to remember something later, you don't want to store it on the chain because it's too expensive or it's too big, then this works quite nicely. Storing keys, caching particular bits of data also works quite well. Network services, of course, oracles, but also actuators. You want to do something based upon what's happened on the chain. You want to open a lock, Slockit style actuators. This can sort of do that. So examples of this specifically, vote counting, constraint optimization for CPU tasks, right? Vote counting, you probably have to integrate with some sort of gamification to make sure that if anyone puts an incorrect vote count, then they can be punished. Constraint optimization, probably don't even need to gamify it because you can check that the constraints were indeed optimized correctly, usually quite quickly. Offloading storage for things like chain archival, like making sure that historical block data is archived and can be paid to be archived. Suspending a smart contract. Maybe your smart contract, you don't need to keep paying the storage rent, right? So you just say, basically, destroy my smart contract, leave a little tombstone that says like a hash of all the data that was in it, and then stick it all on IPFS. And at some point later, you can just pay to have it restored. Also on-chain signing. So stick a bunch of have this off-chain logic. Create a bunch of keys that remain sort of secret, and then have some smart contract or some on-chain logic that says, hey, actually, I want you to sign this data, and you can have it like it to be a threshold multisig, so you've got some degree of shared security. And the chain itself can kind of sign stuff, which is obviously something completely new, because at the moment, all of the data on-chain is public, and therefore they can't hold things like keys. Network services, price feeds, transaction submission. So you can sign a transaction now. You can also submit it. You can like basically write the logic so that your validator nodes or whoever submit it to another network, like for example Bitcoin or Ethereum. And also all sorts of interesting things with like light clients. So you can have the off-chain logic interpret or go off to another network, keep syncing it, and then feed in headers that it purports to be sort of valid, and you can have some gamification to ensure that those headers are indeed valid, and if they're not, someone gets punished. And you'll see, like, quite a bit of this stuff is stuff that we need to do in Polkadot anyway, so this is kind of our abstraction and generalization mechanism for doing it, but it's pretty relevant for other tasks as well. So within Polkadot, upcoming developments, this is quick. How much time do I have? This is pretty quick, anyway. I don't know. 12 over. All right. Well. All right. Cool. Okay. So in terms of developments within Polkadot, and again, this is like pinch of salt. Don't quote me on this 6 months and later, please. The number of validators that we're looking at on Polkadot will be probably between 50 and 100 at the beginning, and increasing to 1,000 or so once it's sort of fully deployed. And those validators will all do basically the same thing: produce and finalize blocks and validate parachains. The collators of parachains are the guys that actually maintain the individual shards, if you like, parachains. They're independent. Chain economics. Transaction revenue at the moment. So if I don't know if you're familiar with Ethereum, 100% goes to the block producer. There is no treasury because Ethereum doesn't have a DAO or anything like that. In our case, 10% is going to go to the block producer, so not too much, just a sort of a little bit. 90% will go into a treasury, and the treasury will fund chain developments, all the rest of it. Maybe conferences like this. There's going to be transaction prices for the relay chain. Probably going to be fairly expensive, basically because the relay chain has an awful lot to be doing other than processing transactions. It's got to manage Polkadot. So the transactions make up a relatively small piece of what it needs to do, and therefore it has to be relatively expensive because there's only a limited amount of transaction volume that could ever be possibly managed. So you're looking at probably between 5 cents and 50 cents for most of the transactions. And the sorts of transactions we expect are things like, stake, unstake, transfer. There's not, that maybe set my votes for the upcoming few council elections, that sort of thing. Not too much. Most of the stuff, in particular voting, will happen with coins that are sort of stored in proxy, but on a parachain, and that'll be much cheaper to be able to transfer and do stuff, because of course the parachain can operate independently to the relay chain, and therefore has much greater transaction volume, and therefore much less costs associated. Block reward, we're looking at probably around 10% in the first, inflation, probably around 10% in the first year, which, given our likely number of validators, probably between 1,000 to 2,000 dots per validator per month, shared out between them and their nominators, however they see fit. I mentioned before crypto. I don't even really need to say it again, but it's going to be used this ristretto schnorr. Yeah, it's like kind of cool new technology, and we will have parity signer support. Oh yeah. And I mentioned this before as well. There's a Huddle Bonus. We're planning delegated voting. I kind of mentioned this as well. So like basically one of the big problems with proof of stake is you don't want all of your validators, all of your like coin holders to basically just pay some guy with a big validation farm to do your validating for you, because you're going to have a monoculture amongst a very large, potentially very large proportion of your validators, which means if there's any kind of flaw systematic in how they're managing the validation nodes, generally in terms of security, but potentially in other things as well, software versions, implementation, whatever else, then you've got a huge problem. And it's a problem, what you want to do is try and sort of incentivize there to be as many different validators with as many different system configurations doing things in as many different ways as possible to mitigate for that. So what we want to do is basically kind of make it more likely that lone validators, that independent validators are going to be using their own hardware and their own software deployments and so on. And that's where we came with this kind of basically minimal punishment for non-threatening bad behavior. So if it's just one validator that's messed up, then it's basically kind of slap on the wrist, but off you go. Whereas if it's like 15% because it's some guy who's running a validator farm and all of their nodes suddenly went offline because they forgot to pay the electric bill or something, then it's like actually massive slashing. I think this is two more. Okay. Second to last one. So admin, very important for validators. I don't know if there's any people who might want to validate here, but I'll sort of tell you what we're thinking. Basically, we want to avoid any risk of token loss with hot staking keys. So what we want to do is make sure they've got different keys for different things, and that the key that actually controls where your dots are and who's going to actually transfer between accounts, that key needs to be cold. So the master account funding key, the thing that controls your dots, is cold. Staking administration is kind of mostly it's kind of warm. You use it sometimes. Maybe it's on like parity signer or something. You occasionally use it, but it's not like on a piece of paper locked up in a vault somewhere at UBS third basement in Bern or whatever. And then for the other keys for actually running the network, block production, grandpa validation, all the rest of it, they're all hot keys. So they're running on a node somewhere. Finally, your reward account will be specifiable, so you can be either rewarded to the validation account and sort of just keep cumulative interest style accruing your rewards, or you can have it rewarded to some other account and like, I don't know, spend a rewards or something. And there will be hot top-up and withdrawal, so you'll be able to basically take out some of your balance without having to completely unstake everything. Okay, final slide. NPOS, what's the latest on that? So we're going to optimize the nominator-validator graph for maximum chain security. I sort of mentioned this earlier, the approval voting and kind of graph optimization thing. Basically, it will come down to you nominate several validators. Only the active part of the stake is paid, so it pays to nominate more validators until, of course, you nominate one that wasn't secure and they got everything slashed and then you've lost all your money. So it's up to you to find that sweet point of, they're probably secure, they're probably honest, but they haven't got quite as much stake as all the others, and therefore I will get paid a greater reward. That obviously leads to a market mechanism, and our specific method for determining who gets whose stake in terms of nomination validation is this guy, Fragmenjean. Fragmenjean? I don't know how you pronounce that. Fragmenjean. I've never seen Fragment. Yeah, but it's an acute, right? Maybe he wasn't French. I'm thinking it's French, but maybe it's something else. Fragment, whatever. So this guy was like, I think he was around in the late 1800s, if I remember correctly. And he came up with this like pretty cool magic way of doing exactly this problem. And everyone forgot about him, including like all the researchers who were trying to solve this problem in the last few years. And then kind of dug up his paper, and it turned out to be really good. So, hey ho. And you get paid for off-chain optimization. So it's like actually, if you think of proof of work as being actually really, it's proof of waste, right? Because you're not working on anything. It's like, because it's wasteful, or you're just solving a pointless problem. So that's not work, that's waste. I mean, I guess it's kind of work, but it's kind of pointless work, therefore wastage. This is actually work. The sort of proof of work that we have here is solving an optimization problem that helps create an optimal mapping of nomination stake to validators who are trying to use that stake and might get slashed because they misuse it. And making that optimization is super important, and so there's a small reward because it's done off-chain, because it's too computationally heavy to do on-chain, and that's actually proof of work. So you can bring that up if someone asks, what did you learn at M1? There you go. There's something new. Cool, that's the end of the talk. Cheers.
Thank you, Gavin.